Thank you all for being here. I'm very excited today to be introducing Rafael Prieto-Curiel. As Jeff mentioned, Rafael is a faculty member at the Complexity Science Hub in Vienna, pretty cool sounding institution. He also works and is consultant for the OECD as well as the World Bank, where he's done a lot of work on a range of urban issues, from violence to mobility, migration, as well as spatial and demographic analysis. In addition to exploring the linkages between urban form and car dependency, the topic of today's talk. In addition, he's also done a lot of, has an interest and has done work on data visualization, communication. If anyone's seen his Cities Moving website, you'll know what I'm talking about, which he'll, I'm sure, introduce today as well. Originally from Mexico, Rafael comes to urban studies via the field of mathematics, which is a somewhat unusual path, no doubt, but one that has borne considerable fruit. I became familiar with his work through a very impactful paper he had published in the Proceedings of the National Academy of Sciences on the urban morphology and spatial patterns of African cities, something of particular interest to me. I felt actually compelled to reach out to him, and he was magnanimous enough to share his code with us, something or an example of how collaborative knowledge production should work across international borders. So again, I'm very excited to have Rafael here, even virtually, and please join me in welcoming him to our speaker series. Thank you.
Thank you very much, and it is my pleasure to be presenting to you. Greetings from Mexico City, although I work in Vienna. I am this week in Mexico City because I came for a seminar here, so it was impossible to be in person in Cornell. But I really want to thank Stefan for the invitation and to you for being sitting there and for listening to my talk. As he said, I'm not an actual urban planner, so my studies on cities are sometimes using mathematics equations, but I will hope that these equations are easy or landed so that it's not like super complicated to listen to. And let me begin with a bit of the two ideas, right? We're going to talk about urban forms, so the shape of cities, and then car dependency, and then I will try to connect them. So hopefully this is interesting for you. Before, Stefan mentioned that I actually work for the OECD, and I have been for like 7 years. And with them, I discovered something that I call the research on Africa, because I work for the West Africa section on the OECD. And let me just give you an idea of how I came across this field, right? I was looking at the number of manuscripts or papers that are published related to different cities in the world. And one of the first things I did is I went to Scopus and I put the names of different cities like Accra, Nairobi, and Cairo, 3 cities in Africa. And then when I saw this, I was very happy. Like, we are publishing since the 80s very few papers related to Africa, but in 2020, like 700 papers on Cairo per year that mention Cairo, right? And that made me really happy. Like, yeah, we're getting knowledge on cities, right? Perfect. And some in Nairobi and some in Accra. So I was happy with this until I put another city for the comparison. I put London just to compare. And then I discovered, well, actually, we reached a point in history where we were publishing as a scientific community more than 10,000 papers per year that discussed London, and only 700 that discussed Cairo or Nairobi or Accra. So for me, this was actually more depressing than not, right? First, because if you ever write a manuscript, and I hope you have that opportunity at some point in your life, you will find that some reviewers, some people that want to actually approve your manuscript or reject it, they will actually use like the case of London. Obviously, we need to do research in London. It's actually like obvious. London is important, right? But then if you write a paper on Accra, do we care enough about Accra? And it has happened to me. I have received feedback from papers that are like, do we care enough about Mexico City? Well, we should, right? And I hope I convince you, not only because, well, we know nothing or very little about African cities, but there's also another aspect. And the aspect is the following. African cities, they are the ones that will experience the biggest change. In Africa, we have a very rapid population growth. So there's a demographic expansion in the continent, much more so than anywhere else in the world. But there's also a process of urbanization. That means people are moving from rural areas of Africa to the cities. Those two combined will mean that most cities in Africa will double the population within the next 30 or 50 years, or perhaps even more. And that is different. Because you see, I live in Vienna, in Austria. Vienna is a fantastic, beautiful city. I love it. There are fantastic cakes. There is nice people. I love it. But Vienna has 2 million people today, and will have 2 million people in 30 years. So Vienna is in a terminal size. That means most of how Vienna looks today is going to be roughly the same in 30 years because there is no more people. If we construct a new building, it means that another building is getting empty, basically. If we put a new highway, then it's basically not even in demand because we already satisfied everything for 2 million people, right? Terminal size is Vienna, terminal size is Roma, terminal size is Milan. But these cities in Africa, they are not. So let me show you just 4 countries. This is in blue, the population that these countries have in 2020, and in gray, the population that they will have in 2080, according to the UN. That is the best prediction that we can have for the population of a country, right? In Ghana, there were 31 million people, but there will be 71 million people in just 6 years. In Niger, they will go from 24 to 126 million people. So they will multiply the population by 5, okay? In Mozambique, they will more than triple the population. In Kenya, they will double the population. And this is what you see in most African countries. And again, if all cities grow exactly the same, then it means that cities in Niger, you expect them to be 5 times larger by 2080. But there is the additional component of people moving to cities. So because of that, cities in Africa will be not even this growth, but even faster, right? We expect an even faster growth in African cities because those 2 elements. So I am convinced that we need to know more about African cities. They are the ones that are changing, not Vienna, not Milan, not Paris. Cities in Africa are the ones that are changing. And of course, data from Africa is extremely challenging. And if you try to do research in London, you Google London metro stations and you download a CSV file with all the locations in 4 seconds. If you want to know the polygon of all the streets, you download it in 4 seconds. If you want to know populations, density, flows, CDR codes, data, interactions, internet, everything, you download it in 1 click. So it's super easy, right? And that's why there are so many papers in London. In Africa, on the other side, data has been very challenging. It's very biased. You have it sometimes only for a few cities. And that is why I want to introduce you to one very, very beautiful data set that was put together by the OECD. This idea of African data, by the way, in this presentation, you will see a lot of photos from African cities. In all of them, I tried to put the name of the city that you're seeing. So this is a beautiful city from Lusaka in Zambia, because I often try to challenge the perspective that people have of Africa. People usually think that Africa is nomadic continent with some villages. No, we're talking about big cities, development of cities with buildings, with infrastructure, with budget, with money. And this is like the pictures that you will see during the presentation, okay? The data that I want to show you is called Africapolis. Africapolis is put together by the OECD. And what they did is, let's take first census data. Census is the way to count people, right? Perfect. The issue is that in Africa, you will have countries where the latest census was maybe from the 80s or maybe from the 90s. So counting people It's extremely challenging if you have this demographic expansion and you don't have a count, you don't have a census. So it's super tricky sometimes to do just census. So what I did is this is the project by the OECD, put together by many governments, including the government of Austria, the government of France, the OECD, USA, many. They put together this project that started around 15 years ago. And the idea was, let's look at aerial pictures of the world. And based on those aerial pictures, let's try to get two things. First, where are cities? So for instance, here you will have where is Kano, where are all the dots represent cities in Nigeria. But second, it tells you some idea of the boundary of a city, right? Defining the boundary of a city is challenging, especially if you ask different countries. You will have in Africa 52 countries. So it's tricky to say, okay, how is the city in Kenya and how is a city in Ethiopia? Because they use different definitions, oftentimes administrative, then it's super tricky to compare, I don't know, population, growth, expansion. That's why the OECD put together this data set. I know that 10 years later, maybe this project sounds a bit easier to do because now we have AI, we have photos from Google so that you can put this in a machine and do this automatically. Yes, I know that this is now easier. But this project was put together around 15 years ago. So 15 years ago, they actually defined the boundaries of cities. And using the boundary of cities, they define it for all cities in Africa, around 9,000. And then they take an estimate of the population using the best possible census plus some demographic expansion. Thanks to that, now we can compare cities, okay? And now we can compare cities already 10 years ago. So now we have data, and this data is producing more spillovers, more data, because again, we need to know more of Africa, right? So for instance, what I did is let's take data from OpenStreetMaps. OpenStreetMaps is this platform in which we crowdsource stuff like roads, where is a market, where is the mosque or the church or the school or something. And we traced actually the highways. These are all the highways in the continent. And you can tell, well, the dots are cities, bigger dots are bigger cities. And this is a bit deformed the map just to appreciate it better. Like Lagos in Nigeria, Kano also in Nigeria. So this is Nigeria, the country. This is the Sahara Desert. This is Morocco, Algeria, or Egypt. And you can tell where there are more highways, like a more grid pattern, like in Egypt, where you have a lot of cities with a very dense sort of network, or Algeria. Everything along the Mediterranean coast is actually very dense and very solid infrastructure. But you can also tell there are parts like Sudan, where there is basically one highway connecting a city, right? So it's interesting. Not only that, it tells you how the city might expand, the connections that it has, how easy it is to get trade out of these cities, how easy it is for you to produce something and take it into that city, how fragile cities might be, because if there's one disconnection here, then maybe you're actually disconnecting cities. It tells you how isolated are cities, how connected the travel time. So we're getting better with these data sets. Just as a warning, if you ever plan to use OpenStreetMap data, remember that it is crowdsourced and therefore it might be extremely biased. What I mean by that is there are some people in Mexico who will be crowdsourcing all the taco places in Mexico City because we want to know where the taco places are, right? So that's why you have taco places. But if you go to another country, you will have that they crowdsource other stuff, for instance, different bars, markets, a mosque, or a church. But that doesn't mean that you have everything, especially in Africa. So once we take OpenStreetMap data, you can tell that, for instance, cities that there are no market inside, well, there are no market in your data set. But obviously there is a market in the city, right? It's just you don't know it. So OpenStreetMap data is getting there. we're getting better, but be careful because there are these gaps and holes. If you're ever interested in this network, you can just download it. It's very easy to work with. It's already connected and it's plugged in with cities. So with that, you can tell like connections, gravity models, and so on, right? It's just a couple of ideas of how to work at the continental level with all the connections from the city. Okay? Then let's talk about urban forms. What do I mean by urban forms? And this is Harare in Zimbabwe. Again, it looks amazing, right? Nobody would say that this is an African city. Let's talk about urban morphology. Urban morphology, we refer to many things. Sometimes people think that is the boundary of the city. It's not. That is one part, a relevant one, but it's also telling you how polycentric is the city, how dense is the city, the layout of buildings and the streets and the grids, and how people travel. All of that is the concept of urban morphology or urban forms, okay? Then how do you say it? How do you measure that? So something super interesting that happened with my colleagues is that Google released the building footprint of African buildings. What do I mean by that? Something that looks like in the left-hand side, that is telling you the location of every single building that has been constructed in the continent. That is amazing, right? Because then you can tell that based on this photo that, by the way, is in Accra, you can tell all the grid, all the buildings where they are, and it tells you the boundary of each building. You can, if you squint your eyes a bit, you will see like the streets, the layout or of the grid of the streets. With that, you can tell the center, the sizes of buildings, the proximity between buildings, how compact they are, the space between them. So the OECD colleagues from there that, by the way, the OECD is the rich, let's say, the club of the wealthy countries in the world. Although Mexico is there, and Mexico is not wealthy, but this is the OECD, right? And with them, we try to understand what is the shape of African cities. We have the boundary from Africapolis, and now we have the buildings. So let's take the intersection of the two. And if you tell me the boundary of a city, I can tell you the buildings that are inside the city, and therefore the buildings that are inside every single city in Africa, almost all of them. The issue is that Google made this with artificial intelligence, and it means they use the contrast between the soil and the ground, let's say, and buildings. Okay, with those two is that they say there is a building here and there is a polygon that must have this sort of shape. In some cities, it's more tricky, especially if the contrast between the soil and the building is not good enough. And oftentimes, for political reasons, they don't include some countries. So if you go today to Google AI OpenStreet data, Open Maps data, you will find that, for instance, China is not included, Saudi Arabia is not included, and Cameroon is not included, but the rest of the countries are included. So it's sometimes almost all of them. Okay, let's say we have them all, especially from 52 countries in Africa, I think we have 49. So we're almost there. We put together this data set and we intersected with cities. And in total, we have 183 million buildings. That means a footprint, separate footprint of each and every single one of them for 5,600 cities. That in total makes 10,000 square kilometers. Amazing, right? This is the first time that we can actually use this data set to understand the shape of cities. To my surprise, you can actually use this data set and see, for example, the size of buildings. How big are buildings? Well, I have no clue, but it turns out that buildings are usually extremely small, especially in Africa, and especially in poorer cities. For instance, in Central African Republic, in Bangui, the average size of a building is around 14 square meters. That, I don't know the number in foot or in yards or something like that, but 14 square meters basically is like a room, maybe medium-sized room if you want, but it's just a room. So it's very small, actually. And that means, although we don't have the height of buildings, because this is just an aerial picture, right? And with aerial picture, you say, where is the building, but it doesn't tell you the height. We don't have the height yet, but we know that if your footprint is 14 square meters, then the possibility that is more than 1 or 2 floors is 0 because it's too small, right? With that, we try to measure things like how round is a city, how compact is a city, how elongated is a city. And the way I described it is, okay, imagine that all the dots here are a building, that I can differentiate the shape of cities between being round and compact, or only round, or only compact, that means contiguous buildings, one next to the other as much as possible, or none of them, right? We measure the built-up area, that is the polygon from Africa Polis. And we measure also, well, whatever you want. You have the footprint of all buildings, right? So I measure things like the diameter. The diameter is the longest distance I can find in the city. Or I measure the average distance between people, the average distance between two randomly selected people in the city, the elongation, the sprawl, and this is how we proceed, right? Considering all the buildings in every city, and then use that to try to quantify how cities are elongated or not, sprawled or not, okay? Then the formula, something super beautiful, and this is where maths start, but I promise you it's just two equations, okay? If I take a circle that the area of the circle is area A, a number A, let's say 7 or 19, and I put two random darts in that circle, what is the expected distance between them? So I put one thing here, the other thing here, I measure the distance, and I repeat that exercise thousands of times. What is the expected distance between those two dots? Well, usually, this formula, I would ask people in the audience if they know it, but I cannot because I will not hear you. So it's a tricky one, but what is the average distance if you just throw darts in a dart bullseye and you randomly pick two of them? It turns out that the average distance of that exercise is a super funky number that is 128 divided by 45 by the square root of A. Now, the square root of A basically is the square root of the area, and the square root of the area is proportional to the radius, right? So what this formula is telling you is that the distances between 2 points inside a circle must grow with some constant. I don't care much about the constant, although it looks beautiful, especially for a mathematician like me, because those numbers that appear in nature, 128 divided by 45 pi, it looks so beautiful, right? It's like intriguing. Why 45? The square root of the area. So it's easy. It's just distances grow with the radius, right? And this is for a circle. The same principle, we want to apply it for a city. I take two random buildings or two random people. Let's say that you live in one house and you want to visit either your mom or the place you work or somewhere. So I can take two random objects in the city and measure the distance between them. The simplest possible distance, the Euclidean distance, that means as a straight line inside that city, right? And I want to use this formula because I know how it works in a circle. Then I want to apply something similar in a city, okay? So what we did is let's use this formula, 128 divided by 45 pi times the square root of something. And let me tell you what is that something. On the left-hand side is the average distance between any two random people in the city, and is the same number times. And what can I measure from a city? Well, I can measure the number of buildings. This is easy. It tells you if the city has this boundary, I just count how many buildings there are. And I say, for instance, Mexico City has 4 million buildings, New York has 4.1 million buildings, and Accra has 2 million buildings. So that is just the number of buildings. If I multiply that by the average area of the buildings, the number times the average, this tells you actually the footprint, how much constructed surface has been constructed in that city. number of buildings, and here is just the average area of buildings. I multiply that by another constant that is the sprawl of the city that I will define later, and then I multiply it by the elongation of the city. So the way to work with this formula is to say the following. First, I measure the average distance between two objects in a city that I can easily do because you already gave me the footprint of buildings. I count how many buildings, I count the average area of those buildings, and based on those three, I define the sprawl and the elongation of the city. Okay? I know it looks weird, but what it's telling you is we're using the formula for the circle. Distances are 128 divided by 45 by the square root of the area. And this formula, again, is super funky, but I love it. Let's apply it for cities. The distance between two objects in a city is 128 divided by 45 by the square root of something. I just decompose it into two multiplicative components. That is how much has been constructed in the city, number of buildings times the area, and then two other multiplicative components, an index that usually will be between 1 and something else, 1 if the city has no sprawl, and 1 for the elongation if the city is like super round, and larger coefficients for sprawl and elongation will just make the city have a different form, okay? So the principle is just, let's look at circles and you define the form based on those formulas for the circle, okay? The formula, I love it so much. I was about to get a tattoo for that formula. I haven't, but I really think it's like a cool, super funky formula. But what is the interpretation besides the actual cool formula? Let me give you a bit of the sprawl and elongation. And this is beautiful Nairobi in Kenya. This is the important part, that based on the distance between buildings in the city, I could define how sprawled and how elongated are cities. So now I'm showing you 9 cities in Africa. I plot them at the same height, so with the same zoom to the buildings. Every dot that you see here represents a different building. So Embu is purple with all the buildings there. Kaduna is red with all the points representing buildings. They are almost the same population. So I'm not taking Lagos with 20 million people, and I'm not taking a town with 20,000 people. I'm taking roughly cities with nearly 2 million people. And what you can see before going to elongation and sprawl is that you have Kaduna in the left bottom, super compact and super tight next to each other, right? But you have Hawassa in the right top that looks like much more sprawled, much more disordered. So this is exactly what it's measuring. Elongation, if we are on the left-hand side, it means the elongation is very small. Cities are almost a round shape. When we move to the right-hand side of the city, cities become like a chorizo or like a sausage. And then if we have a very large elongation, we end up with something like Kigali. Imagine if you live here in the top part of Kigali, and you want to travel to the bottom part of Kigali. It's going to take you hours, because I know that in Kaduna, it takes you only like 40 minutes to travel. If this is 40 minutes, then from here to here, top to bottom of Kigali, that is going to take you around 4 hours, right? This is the cost of elongation, because cities are getting like a sausage form. Now from bottom to top, if the city is in the bottom, it means the city has a very small sprawl. So the city is tight, things are almost next to each other, right? And you can tell that there are almost no blank spaces in Kaduna. But then as you move up, cities become like more spacious between them. So you see in Embu, all these white dots and all these white entries that represent spaces where the city has not been constructed. Now, if you combine those two, you see on the top right, Hawassa, sprawled and elongated like a chorizo, all the distances are super large. In the bottom left, round and compact, because Kaduna is almost round, all super compact and tight. And this is the way we want to observe cities. Imagine in this diagram, I put all the cities in Africa, and then we measure how are the sprawl, how is the elongation, how are the distances between people. And one of the interesting results, besides this idea of let's measure the elongation, remember, from round, like a tortilla, to elongated, like a chorizo, and sprawl, from compact to being extremely sprawled. The results are the following, and this is the interesting bit. I take the 6,000 cities in Africa. Here in this diagram, every dot represents a different city. In the horizontal axis, I put the population of those cities on a logarithmic scale, okay? And in the vertical axis, I put the number of buildings that I found in that city, also on a logarithmic scale. And here the color represents the region in Africa. So red is North Africa, that means this is Cairo. Green is West Africa, that means the second dot from right to left is Lagos, and so on. Every one of these dots represents a city. Now, what you find when you put log scale, so both axes are on a logarithmic scale, is that I can roughly express the number of buildings in a city as being proportional to, so this sign that you see that looks almost like a Greek alpha, that means proportional to the population, but the population has an exponent that is 0.98, is almost 1. If the coefficient was 1, it's telling you that the number of buildings and the population, they grow at the same speed. For instance, 1 building for every 4 persons. If you have 100 people, then you need 25 buildings. And if you have 100,000 people, then you need 25,000 buildings. But the interesting bit is that it's not linear. It's slightly below the coefficient 1. And this, when you study cities, is talking about the scaling, how population affects the number of things. It's slightly below 1. That means in bigger cities with more population, the number of buildings is slightly smaller than if it was linear, because this number is slightly smaller than 1, right? So they get a slightly smaller number of buildings. Perfect. So this is normal because you would expect that larger cities have more buildings, but that number gets slightly smaller, almost 1, but not really 1. Then the area of buildings, right? Remember that we have the area of buildings as an element. Here I have again the population in the log axis, the average area of buildings in the vertical axis. And you can tell based on this regression that the area of buildings is slightly above 0. Again, I can express the area of buildings as being proportional to the population times a coefficient. If this coefficient was 0, then it would tell you that the area is proportional to 1, because any number to the 0 is 1, right? And if it was proportional to 1, it means that the average area of buildings does not depend on population. However, we find that it does depend slightly. And bigger cities tend to have slightly bigger buildings. This is cool, right? Because now we have 2 at the same time. They have more buildings, but slightly less than linear. And they have bigger buildings, slightly above linear. Perfect, right? So they get bigger buildings, bigger footprint of buildings. And this is normal, actually, if you think about it. When you go to a small city or a town or a village, you will find that the buildings are actually short, right? And the buildings are actually small. But then if you ever go to New York City, that I love, you will see these gigantic skyscrapers and gigantic buildings. We are only using the footprint because I don't have the height, but still you have a bigger footprint in bigger cities. Now for the sprawl of cities is proportional to the population to 0.011. That means basically bigger cities are almost equally sprawled as small cities. Maybe slightly bigger, but it doesn't really matter this 0.01 because it's close to 0. So it tells you the coefficient of sprawl. Again, I express it as population to the something is almost 1, it's almost constant, right? Here in the horizontal axis, population, and in the vertical axis is the sprawl. And finally, what about the elongation? So the elongation, if I put population and elongation, I get that the cities get slightly more elongated if they are bigger. They are slightly more deformed when they grow. Perfect. Now, we know what is the effect of population in terms of urban forms. This is the important part, right? And the effect is the following. Now that you have the whole elements, remember that I can tell you, based on the distance, the number of buildings, the area of buildings, the sprawl of cities, and the elongation of cities. This is why we call it the base model, B-A-S-E, base model. And the distances in cities grow almost most of it because of the higher number of buildings, a bit because there is more area of buildings, so buildings get larger, a bit because of the sprawl, but almost nothing, and a bit of the contribution comes from the elongation. So I can express, remember that the distances in cities is 128 divided by 45 pi, the square root of BASE. So the square root means I can plug in population to the 0.98 times population to the 0.67 from the area, times population to the 0.11 because of the sprawl, times population to the 0.05 because of the elongation. And when you put the square root, that means take the coefficient and divide it by 2. Excellent. Distances in cities grow, again, alpha proportional to population to the 0.532. This result, I think, is beautiful because it tells you the following part. Distances in cities grow almost with the square root of the population. Okay? So what? Remember we have that distance is this beautiful formula, the base formula. Well, distances grow almost with the square root of the population, even a bit more, 0.53, not 0.5, right? So distances actually grow with the square root of the population. So what, right? What is the use of that formula? Well, a lot. Now we can compare distances between cities. So let me give you an example. I have on the left-hand side the footprint of all buildings in Jakarta, in Indonesia, and on the right-hand side, the footprint of all buildings in Kigali, in Africa. And again, you can tell very beautifully the main highways in Jakarta, where the boundaries of the city is. And I plotted these two cities with the same height. So again, it's the same zoom. That gray boundary, gray bar that you see in the bottom are marking 20 kilometers. And you can tell that there is something very weird, right? Because on the left-hand side, I have Jakarta that accommodates around 33 million people. And on the right-hand side, I have Kigali that accommodates only 2 million people. So now we can actually try and compare distances and observe, well, yes, maybe you're far away, but because you're in Jakarta, actually things are super close to each other. Actually, Jakarta is one of the most compact cities we have ever found using this technique. Whereas Kigali on the right-hand side is one of the most elongated and sprawled cities. Distances are almost the same between the two cities, but Jakarta has around 15 times more population. So then you can have an idea of how remote you are from the city center. For instance, here I mark with concentric circles, something that now is comparable. Remember that distances in cities grow proportional to the square root of the population. So whenever you measure how far you are away from a person to your work or to your mother or to the restaurant you want to visit, whenever you want to measure those distances, you have to take into account the city where you are, and you discount that factor if you divide by the square root of the population of that city. That is what I did here. I mark a circle where it is the remote location in Kigali, the dashed circle that is there, and the same circle proportional to the population in Jakarta. And you can tell that everything fits inside the circle in Jakarta, but almost nothing fits inside the circle in Kigali, right? So that is one of the implications. You travel much more, you pollute much more, you need more energy. You disconnect people. Traveling from one extreme of Kigali to the other takes hours, and most of the people cannot travel for hours, not daily. So therefore, this is creating disconnected cities. Furthermore, in Jakarta, you have infrastructure. You can tell that there are roads and highways and the metro and public transport. In Kigali, there is none. So traveling from one side of Kigali to the other is almost impossible, right? And that is why urban forms are a critical element of the future of cities. Remember that this city, Kigali, will double or triple its population within the next 30 years. So we need to think of ways of accommodating 3 times more population here in a way that we make it more sustainable, right? Now, what about other urban forms? And now a picture of Luanda in the coast. This is amazing Luanda, by the way. Let's discuss other urban forms. And I came across, maybe you've seen it, the line in Saudi Arabia. The way I came across the line was through Instagram. I was just, browsing my Instagram, and my Instagram usually shows me pictures of dogs, cats, recipes. And then it showed me a render of a city. And I thought, this has to be a joke. This has to be an actual joke, right? And no urban planner would ever make such a stupid plan for a city. But guess what? They did. It's not a joke. In Saudi Arabia, they are constructing a city called The Line. It has been stopped. It's controversial whether they are actually following the plans or not. It's debated. But anyway, the plan for Saudi Arabia is that it's going to have this city called The Line. And some of the attributes is that it's going to be 500 meters tall, so taller than any construction in Europe. It's going to be only 200 meters wide, so it's like a super tight city. But the most relevant part of The Line is that it's going to have 170 kilometers long. For comparison, 170 kilometers means traveling from one side of Italy, the boot of Italy, to the other. Like it's crossing the whole country just to travel 170 kilometers. What is the cost? Well, we know because of the base formula, right? Again, we can go to this expression and see, let's put the number of buildings to the area of buildings because it's 2 lines. The area of buildings, we can measure the footprint, the sprawl is close to 1, but the elongation is the record of the highest elongation in a city. And that's why the average distance between 2 people in Saudi Arabia, The Line, is going to be around 63 kilometers. So it's not possible. And not only that, the time that it will take you to transport between one point of the city to the other, although they say we will put the super fast train and whatever, we showed mathematically that you cannot, because for a train, you need to add stops, right? Otherwise, people cannot get on and off the train. We counted what happens, how many number of stations is the optimum, and this city that they are constructing actually will be a very, very slow city in the world. Now, I will tell you more about The Line in the next part. Harare in Zimbabwe, nice city. Why are some cities sprawled? So that is a relevant question, right? But now we can observe in Africa, cities are being sprawled because they are constructing through the highways, and that's why they are getting those shapes. But why are cities sprawled? And one of the main reasons, especially in some parts of the world, is because cars. I think they are one of the biggest enemies for urban planners, and I hope you see them as well as a very challenging part. Car industry has made you believe that the biggest burden of cars is the petrol that they consume, right? Because they know how to get rid of it. So car companies, they usually don't want to talk about any of the other burdens that they create, that are many, because they know that they can get rid of one element of cars, that is the petrol. If I give you an electric car, now we sorted everything, right? But it is not. Cars, for instance, here I have a comparison again on the same scale. Florence, a beautiful city in Italy, versus the interchange in Atlanta. In the left-hand side, you have people living, thousands, in a beautiful touristic city where you walk around. On the right-hand side, you have cars and road accidents, noise and pollution. Here I have a highway that I believe is Houston. And cars, they get like a lot of space. And that means every time I go to the US, I was a few years ago in Dallas, and I try to walk around in Dallas, and it's such a challenge. I don't know how people can do it. Well, I know you don't. You cannot walk because there are no pedestrian space, right? Every time you get more space for cars, you are getting rid of space for cyclists and pedestrians, so you don't do it. Here I have a super interesting photo of the center of Las Vegas, where in red is all the parking spaces in the city, and in gray is all the highways in the city. In the center, 32% of the city is parking spaces. So that means if you throw random darts in the city of Las Vegas, there is a 50% chance that you will hit car infrastructure because of the highways and because of the parking spaces. Cars, they create road accidents. 1.3 million people are being killed every year because of road accidents. 50 million people, the size of Colombia, the country, is being seriously injured in road accidents every year. Cars have killed more people than the two world wars combined. Cars require tires, and people usually don't think of tires as an element of cars, but they are one of the most pollutant substances that they are. When you buy a new car, the tire is like all fat and like pointy. And when you use the car, the tire gets thin, right? Where does that go? Well, everything on your tire will get either to your water or to your lungs or to your food or to your plant or to the oceans. So all of that thing, that ends up in our system, right? And if not, we put them in piles like this that usually get fired, and we cannot even put them out because fires are so toxic that we actually just let them burn. In the world, we are producing around 3 billion tires each year. And this is something that obviously the car company will never tell you, right? Because they cannot get rid of tires. They can get rid of petrol. When they get fire, you can see the fire from the moon, actually. And something super depressing is that the best solution that we have found, obviously, some people will argue, oh, with the old tires, we can construct basketball courts and beautiful football pitches or whatever. Yeah, yeah. But 99.99999% of the tires, they end up like this. We put them usually now far away in different plots of tires, just in case one of them gets fired. Not everything burns down. It's super depressing when you talk about tires. Cars, to be honest, they all look the same to me, especially nowadays, all the SUVs and all the cars. There are some cars that have a tiger in the front or a horse or I don't know, different symbols. I don't even recognize them, but they look the same. We have actually culturally flattened even the shape of the cars or the color of cars. This is the color of cars since 1946 up until 2020. And you can tell that before, at least 70 years ago, we had color in the cars like yellow, purple, blue, something. But today, cars are almost all of them in a gray, black, and white scale. Silver. Some are still the brave people that use the red color. But when you see actually a parking space, today you see this number of cars that are on a grayscale, and today around 80% of the cars are on a grayscale. They look the same. You're driving the same. It's just one of them costs $20,000, the other one costs $40,000, but you're basically driving the same apparatus, right? Not only that, cars are getting bigger, and this is shocking. You see the same model of car, a BMW, used to be 252 meters, now is 454 meters. It used to weigh 1,000 kilos, now it weighs 1.6 thousand kilos. Bigger and bulkier cars. But what it means is that you're manufacturing effectively 1.6 tons of materials for you to have a car. There is no way this is sustainable, right? Just the manufacture of the cars is way above our CO2 budget. Not even if you try to put some trees somewhere. No. It's 1.6 tons. And the same happens with almost all the models of cars. You would assume that cars are getting bigger because now we are driving with more people inside the cars, right? Well, it's the opposite. Actually, cars are getting most of the journeys on a single passenger. With that, the cost of a car is around, any estimate? Having a car costs 600,000 euros. When you compute how much does it cost to own a car for 50 years, a person is paying almost, in Europe, 1,000 euros per month for owning a car, creating one of the biggest financial burdens in society, more expensive so than owning a house. But there is a positive side if you are a car driver. Around 40% of this is actually paid by society. So you don't have to pay your 600,000 euros. 40% of that will be paid by taxpayers who have to pay for your traffic lights, for your accidents, for the asphalt of the roads, and for everything. And obviously, it's talking about manufacturing, it's talking about jobs, it's talking about politics. And I honestly challenge this side. You have many politicians, both in the US, in the upcoming elections with Tesla, for instance, or in Germany, talking about cars and being proud of them. Yeah, because these car companies are sponsoring the campaigns, not because they are the solution for anything. It's just when you talk about cars, you're also talking about politics. For instance, here I have a photo of the Mexican president, former president. He's out of the office since the past 3 weeks. And he was super proud that Elon Musk was constructing one of the biggest Tesla factories in north part of Mexico. They sponsor campaigns. This is the reality of cars today. For comparison, in 2019, just before COVID, if you count number of births minus deaths in the world, we grew in population 78 million people. In the same year, we manufactured 83 million cars. So we are actually growing faster today in cars than in people in the world. If you see this is a super depressing chart because it tells you from 1980 up until 2022, the number of cars in Mexico, the country, the number of public transport, that is that teeny tiny yellow line that you see, motorbikes and cargo, depending on the color, right? Something shocking. In the year 2000, there were 10 million cars in Mexico. By 2022, we have 34 million cars in Mexico. 34 million cars. That means the number of cars more than tripled in the country in just a few years. Actually, there are so many cars today that people started switching to motorbikes. I know that I'm talking to people from the US, colleagues, hello. Something super depressing that happens is that when a person from the US buys a new car, oftentimes electric, because they think they are polluting less, the old car is most of the times sold for a cheaper market. And the cheaper market for you guys in the US is us in Mexico. So we estimate that around 8 to 10 million of these cars that we have today in Mexico were actually previously owned in the US. The burden of that is that when you think, I'm going to buy an electric car so that I pollute less, well, your old car is still polluting just in Mexico, so not at all solving anything. This is a photo from Mexico, and that is why we need to connect urban forms with cars. This is Mexico. Imagine a highway, like the one that you see in the photo, with 18 lanes for cars. Come on, this is the issue, right? When you see the photos of those aerial pictures of the city, why it got so sprawled, why is it growing like this? Well, this is the issue, that a lot of the infrastructure that we have in the space in between buildings is actually devoted for cars. So let me talk about car dependency, and this is Dar es Salaam in Tanzania. Let's group, just to discuss car ownership, let's group different modes of transport. If we move by walking, cycling, skating, or something, we call it A for active mobility. If we move by public transport, tram, metro, bus, BRT, and something, we call it B. And if we move by car, either car, taxi, Uber, somebody drives for us, we drive our own car or whatever, we call it C, right? So you can tell that this is the A for active mobility, B for bus, and C for cars, and is the ABC of mobility. And we can represent the mobility of a city in this triangle. It looks tricky at first, but it tells you, On the right-hand side, the number of active mobility journeys. And here I have, for instance, Utrecht in the Netherlands. In the Netherlands, the number of active mobility journeys, people cycling usually, is around 74% of the mobility in that city. People using the bus is around 4%. There are not many bus journeys in Utrecht. And people moving by car is around 22%, right? And we measure the number of car journeys here in the bottom axis, the number of bus journeys or public transport journeys in the left axis, and the number of active mobility journeys on the right. I can represent every city, like Mexico City, where I am today, as a dot in this triangle. On the right-hand side is 34% is active mobility, much less than Utrecht. More public transport, 45%, but even less car journeys than in Utrecht. I can also show you Quito, Sydney, or Portland. So we can represent cities and the way they move in this aggregate as a dot in the triangle, okay? They all have to add to 100%, so that's why we can represent them inside the triangle. Now, what I did is I took the data for 1,000 cities, and it took us like a year to compile the data, but 1,000 cities look like this. The color represents the continent, the size of the disk represents the population of the city, and you can tell super interesting patterns. First, here on the left-hand side, you have bigger cities, and on the right-hand side, you have smaller cities, right? You have Europe, red, spread all over, from very active to very inactive cities, from a lot of, a few cars, like 20% of the journeys by car in Paris, to almost 85% of the journeys by car in some cities. Now, in blue, the light blue is USA and Canada, and you can tell that almost every metropolitan area in the USA has more than 90% of the journeys by car. It's shocking, eh? For when I was looking at this data, for me it was shocking. Latin American cities like Mexico City actually are more like in the center. And something interesting, because I'm presenting to colleagues in Cornell, Ithaca is there with 20% of the journeys by active mobility, 7% by public transport, almost non-existent, and up to 73 journeys by car. So something interesting, because I was looking at this data yesterday, is that Ithaca is, from the US, the city with the highest number of active mobility journeys. That means in the context of the US, I would say that Ithaca is like the city with the highest active mobility. And just the way I would see it is like so, right? A lot of people working, cycling, and running. Although it's not so much if you think about it. It's only 20%, but you have the rest of the world with much more active mobility journeys, right? Something interesting also, we can see it from a map, and here is the same data. The size of the disk is the size of the city, and depending on the share, you have blue dots like Paris, a lot of public transport, or London, a lot of public transport. Yellow means more active mobility in some cities like Cologne or Bern. Red means more car journeys. And there are super interesting factors here. On the right-hand side, on the Eastern European countries, they are usually poorer countries than the wealthier western part of the map. And in less wealthy countries, you have more public transport. In the north, you have more active mobility, and in the south of Europe, you have more car journeys. In the USA, it looks something like this. So every dot is in the US a red dot, meaning almost all the journeys, except for a few cities, are by car, right? And here we have Ithaca, that, by the way, was not in the route of Forrest Gump, but still, I use the Forrest Gump analogy because he passed actually through Syracuse, I think. Something interesting is, again, let's look at the impact of city size. In the horizontal axis, I have the population, and here is a city with 100,000. The second number is a city with 1 million, and on the right-hand side is a city with 10 million, right? So in the horizontal axis, we have the average size of cities in a logarithmic scale. And in the vertical axis, we have the modal share. For small cities, 33% of the journeys are active mobility. But when the cities grow, not in the US, because this doesn't happen in the US, unfortunately, but when the cities grow, active mobility is less easy because distances are very long. So you don't walk when you have to walk 10 kilometers. So that's why you have this decrease in the number of active mobility journeys. But again, outside the US, the number of car journeys for small cities is around 10, 20, 30, 40, 50, 60% of the journeys in small cities are by car. But that for very big cities decreases to 30% or even less. In Tokyo, only 10% of the journeys are by car. So we have this interesting effect where small cities are more car dependent. In big cities, not in the US, we have a much bigger share of public transport, up to 50 or more percent, like in the case of Tokyo, or 45% as in Mexico City. If you're interested in this data, we have this website that Stefan mentioned a few minutes ago, the City is Moving. You can visualize it, it's interactive, you can click, you can download the data. If you have more cities, we can add data, so we depend on collaborations. And finally, I just want to mention what is the burden of sprawl, right? So what we know now, just to summarize a bit, we care for the shape of cities. The shape of cities in Africa, for instance, is super challenging. They will demand a lot of growth. Cities are growing 4 times. A bit of this growth is related to population, but related to the shape is talking about the car dependency, is how we move, because how we move is determining how we grow as a city, right? So let me show you a couple of super interesting results. In the horizontal axis, we measure how sprawled are cities, and here you're observing a result for over 100 cities in the world. Very unsprawled cities, so very compact and round on the left-hand side, and very sprawled on the right-hand side. And in the vertical axis, we measure the percentage of houses with access to pipe water. I know that access to pipe water is almost as a given thing in some countries like the US, so it's not something that people tend to think about. But in other poorer parts of the world, it turns out that not everyone has access to water. And what this figure is telling you is that by the city center in Latin America, 80% of the houses have water, or more, 90. Yeah, in Mexico City, everyone has pipe water, right? But when you move out of the city, the probability that you actually have access to pipe water decreases to almost 30%, and that is Latin America. In Asia, in the center, 60% of the journeys, 60% of the households have access to pipe water, but that decreases when you move away. In Africa, from 50% to 30% of the people having access to pipe water. And the same happens with sewage. So 2 interesting things to look at, and the cost of this sprawl is in Latin America, almost everyone has access to sewage. But see, for Asian cities, not in China and not in Saudi Arabia, and in African cities, the farther you are, the less likely you are to gain access to water and to gain access to sewage. And that is the cost. Again, Africa will more than double its population within the next 30 years. Cities are growing in a way that is usually putting people outside in a sprawl way. And in those locations, it's going to be almost impossible to give them access to pipe water or to give them access to sewage. Access to both when you're in a remote part, well, then now there is no infrastructure. There is no big pipes. There is no way to bring you water or to bring you sewage. And that is why we need to really carefully consider how we are constructing cities, right? Remember, the sprawl means more pollution, means more travel distances, means more segregation, means more car dependency. People that live in remote parts, even here in Mexico City, are more likely to travel by car when they live far away, because that's the way you have to move, right? So that's why urban sprawl is one of the biggest enemies that we have now in cities. And it reduces your access to water, and it reduces your access to sewage, right? And that is critical for African cities. So finally, for some references, just in case you're interested, and I will just show you a couple of slides with some of the papers. One on the African cities, the shape. With that, there are many others that were policy papers with the OECD, super interesting, related to green areas, blue areas, how cities should grow, policy implications. We're working with mayors from African cities, with a couple of them very punctual to say how cities should grow. About the line, in case you're interested. And in case you're interested also in mobility related to the ABC, the triangle that you saw, or why we're interested on how to change it, a couple of mathematical papers here that is a tragedy or a paradox, and I hope you like it. If you have any questions, I'm happy to answer them. And if not, you can also contact me through Twitter or any other social media. And with that, I say thank you. And again, Stefan, thank you so much for having me today in Cornell.
Thank you very much, Rafael. Fantastic talk. Really appreciate it. So we're going to open up for some Q&A. Looks like we have 20 or 30 minutes of, or anyone online as well.
Hello, my name is Tien. Thank you for that talk. I'm a first-year MRP student, and I was wondering, with the elongations of these cities, how much do you consider the topography of the natural landscape? Does that also have an impact on infrastructure? For example, if there's like rivers and mountains, how can people get around if there's actually physical barriers? Okay, thank you.
Thank you so much for your question. Definitely is one of the relevant things, right? When you see the topology of, I show you Kigali, you would think like, people are crazy, why are they building here? Yeah, but it's surrounded by mountains. So you're seeing the valleys of between every mountain as like the tiny stripes that go out of the city. Natural barriers like mountains, a lake, a river, or the coast, they do increase elongation. And they are usually in the form of forming a slightly longer elongation than if the city had no natural barrier, right? In an ideal scenario, the city would start from scratch, growing in a circle, and the circle just grows without any barrier. But that never happens. Usually you want to construct your city close to a lake or close to a river, and therefore you will encounter these barriers. It does increase the factor of elongation, but it does not explain all the factor of elongation. Actually, it explains like 10 to 15% the presence of a barrier. And we compared it by measuring the elongation of all the coastal cities in Africa versus the elongation of all the non-coastal cities in Africa. And of course, the coastal cities, you have half of it is the ocean. So the city gets, instead of like a circular shape, a D shape, right? Like the letter D. Because of this, you have obviously higher elongation. Sure, there is that effect. However, it explains just a small amount. Other barriers like valleys, mountains, and so on, they also explain how the city actually grows. What we did is with colleagues from the VLR, that is like the NASA from Germany, we actually measure differences in height. We try to measure the height of buildings, but not punctually, but the average, and the difference in the terrain. And we also observe that if you take the highest point in a city in the terrain and the lowest point in a city, again in the terrain, you can have very flat cities where the difference is very small, or very fractally cities, very scarp cities. And in very scarp cities, the elongation also tends to be longer, right? So it's true that all those barriers, mountains, lakes, and so on, they create more elongated shapes. However, again, it's not because of that. Most of the elongation is explained in Africa because they are constructing most of the houses next to available infrastructure that is already the highways. And that the lack of planning is what is creating these extremely elongated shapes, not exactly because of the physical barriers, right?
Hello. Oh, okay. I didn't know I saw it. Thank you for your talk. I really appreciate all the original research that you presented today. My question was, I know that green technologies are on the minds of a lot of planners working in Africa. Specifically, you showed Kigali, which I know is trying to really I guess, rebrand itself as sort of like a hub for green technologies in many ways that Singapore has done in East Asia. Are these sorts of conversations about density and the effects that it has on the environment, are those conversations happening in these cities among African planners?
Yeah, definitely. Thank you so much for your question. I'm sorry, but I didn't catch your name.
Oh, sorry. I'm Luke Early. I'm a first-year master in regional planning student.
Perfect. Thank you so much. Thank you for the question as well. Yeah, no, definitely they are happening. I believe that as in everywhere, you have a pendulum of policies. And a pendulum, let me take the US as an example. We have Barack Obama as president, and then goes to Donald Trump, and then it goes to Joe Biden. And this pendulum is like switching between one thing and the other, right? Frequently, you observe that happening in policies, especially at the local level. A mayor puts some rules against cars, and then the next mayor sees the opportunity to use that frustration from drivers to get elected and get power, and they switch in a pendulum to the other sort of side of policies, right? And that is very tricky because as a society, we should be aligned. Do we need cars? No. Do we need pedestrians? Yeah, we need better space, we need more green areas, we need so that this should be more on the technical side where policies don't change much just because of the party we elected. In my case, with African urban planners, we have had super interesting conversations, especially with mayors from cities in Ghana, for instance, in which we discuss and we share with them the data, the progression, the forecast of your city, and we try to explain and work with them also to understand how is their view. And it's been super interesting to observe the reactions towards these ideas because they agree this is problematic. The city is going to grow a lot in the next few years, so we need to do it better. And the way to do it better is perfect. This is in paper, like let's say in my paper, of course. But then when you go to on-site, and we were a couple of months ago with a mayor from an African city, and he was showing us this is the condition, we don't have much road infrastructure. People are building informally in the peripheral parts of the city. Yeah, perfect. But then let's build more formal, slightly taller infrastructures, bigger, so that they are more resilient towards a big drought or a big rain, so that you don't have to reconstruct every single time. And it is true, like they do have a change, they do have a policy, and hopefully this means a vision of how we should look at cities and how we should construct cities. Actually, I usually, when we discuss this, we mention the mistakes we did from the past. And those mistakes we did from the past frequently come from examples in the US. The mistakes we did from the past is the growth of the suburban areas in the US that increases car dependency, that decreases the likelihood of public transport. And that is something we need to avoid for the new cities. Fixing the US is going to be extremely challenging in terms of mobility and urban planning. But fixing something that we haven't constructed is going to be much easier, right? So that is a bit the idea that we have, learning from the past to make it better in the future. I hope I answered your question, Lou.
Hello, can you hear me okay? My name is Stella Connaughton. I'm a first-year MRP student. That's me from behind. Oh, wow. So I was a transportation planner for 2 years before starting grad school, and a lot of times when we were modeling mode choice, we used travel time as the determinant. And I noticed that in your models, you use distance as the metric for determining sprawl and accessibility. I was wondering if you've looked into how travel time specifically relates in the base model, or how travel time correlates to distance from getting from A to B.
Definitely. I think travel time, it is by far the most important element that we need to look at when we think of how we move in cities, right? So if it's okay, let me share my screen for a second again. So let me just show you a couple of slides on the impact of precisely looking at travel time, right? And this, I hope, by the way, the picture here is Medellin in Colombia. And let me talk about travel time. This is going to be a bit mathematical modeling. And this bit mathematical modeling is the following. In the horizontal axis, let me give you the number of car users that you have in a city. So if there are no car users, you're in the left-hand side. If a city, let's say, has 1 million people and you have 250,000, then you're here. And if everyone in the city uses a car, you're in the right-hand side. In the vertical axis, I put travel time, because again, I do consider that travel time is the most important factor, right? For modal share is I'm moving the faster one. So I totally agree with you. And the simplest possible model is a line, a straight line for modeling this that says, if there are no car users and you drive, you decide to drive and you're the only driver in the city, this model is telling you you're going to commute in 15 minutes. But then if there are more people driving and there's 500,000 people driving in the city, it takes you 40 minutes. And if everyone in the city decides to drive, then it takes you like 80 minutes to get to your destination, right? And this model is the simplest way I can try to get the effect of congestion, right? From left to right, less car users to more car users, and in the vertical is travel time. The same happens with public transport, pedestrian cycling, walking, and so on. If there are almost no public transport users, then it takes you, let's say, 50 minutes. And this is just a model, but I agree with you, and let me show you why it's important. If everyone uses the public transport, then it takes you more. And there is some degree here with higher number of public transport users, more time, right? Now, in this very simple model, I'm going to ask people to choose whether to drive or use the public transport. They can only choose two of them, right? If I do that, I can represent from left to right the number of car users, and then from right to left the number of public transport users, right? So everyone has to choose. And here, if I'm in the left-hand side of the diagram, then it means that here, then it means that almost everyone is using the public transport, and public transport takes you 50 minutes. If you were the one who drives, it would take you only 15 minutes. If the city was here, then it's telling you 250,000 people decide to drive, and then from right to left, 750,000 people decide to use the public transport. For those who drive, this is the expected travel time, 30 minutes. But for those who use the public transport, this is the expected travel time, and it's 50 minutes, right? Then, if we are, let's say, here, now cars take you like 70 minutes, but public transport takes you only 50 minutes, right? This model, imagine that the city was here for a second. What it's telling you here is that public transport takes like 1 hour to get to your destination. Driving takes like 30 minutes to get to your destination. What would you do? Well, if the city was here, why do I spend 50 minutes if I can spend only 30 minutes, right? This difference for me is a burden. So some people who use the public transport might decide to switch to using a car. But when some people switch to using a car, the city moves slightly to the right-hand side. So whenever you're here, there are motivations for moving to the right-hand side because cars are faster. If you are here, now cars are slower than the public transport. So you have motivations for moving to the public transport, right? This is a way to observe something that you would move a bit to the left and you would form something that is called an equilibrium. Here, an equilibrium, you can think of it as a Nash game. Nash, in the sense of the Nash mathematician, that says you cannot improve your travel time just by yourself, right? Cities are in equilibrium, not so much, but this is the way we can observe why some people switch from public transport to using a car, and they do it because cars are faster, because cars are more efficient, because cars are getting you to your destination safer, faster, more whatever, right? So if you want to think about the burden, let me take this figure again. And how do we get rid of cars? Well, let's make them more costly. How to get rid of cars? Let me delete this for a second. Imagine that I take, for instance, public transport and I construct a new metro line. If I construct a new metro line, I will decrease the travel time. So instead of having 700,000 car users, I will actually have fewer car users with less travel time in the city, right? So I made the city faster by constructing a new metro line. Also, we can think of different policies. Get rid of a car lane, for instance, and that actually works quite well. Getting rid of a car lane means you're going to increase travel time of cars, right? Because now driving takes longer. So when you get rid of a driving lane for cars, you get something like this. You also get rid of some cars. You get rid of some cars because you were here and now you're here, right? So you get this reduction of cars. However, at a cost. The average travel time was this, and now the city is slightly slower. So this diagram, I find it super useful for trying to model switches in modal share. And as you said, it's because of travel time, right? And this helps you model in a very simplistic way. And I know this is the way mathematicians think. Let's do the most simple possible case. A straight line. I'm very sorry, for very random reason, my computer decided to restart right when I was showing you the slide, but I was finished with the explanation of travel time. So thank you so much for your question. I hope you can hear me.
Yes, you're
thank
back.
you.
Thank you.
Definitely.
Hi, thank you so much for your presentation. I'm Shreya. I'm a first-year MRP student. I have a question on, with the existing model, how can we integrate something like microtransits in? Because in the United States of America, a lot of cities are adopting towards microtransit systems, and that's more of like an in-between the car metric and the user walkability metric. And I was just trying to figure out how to get in between that and add. How would you visualize a microtransit metric in this?
Thank you so much for your question. I really like it. When we were designing the triangle, we had those challenges of thinking different modes of transport and how to aggregate them. And it turns out that we found e-scooters, electric bicycles, electric motorcycles, and other forms of microtransit like this, almost like a bicycle that is slightly motorized. And we weren't sure where to put them, whether it is active mobility, because you use a bit of your energy, or if it's a motorbike, but it's already like using petrol, that is almost like a car, right? We decided for the model to do the following. Motorbikes go into C, the category C for cars, because really they are basically like an individual size car. Bicycles, even if they are electric, we decided to put them into the A category because really they don't require so much infrastructure because you can use your energy to move the bicycle. And e-scooters, as well, we put them into the A category, as in you're using your energy for moving. It's not perfect. And I am aware that we can first open more categories. Instead of saying like the A for active mobility, B for buses, and C for cars, we could also put E for all the electric devices that we use for moving, right? But what we decided is, if I give you 4 categories, now I can no longer represent that in a triangle. So the visual aspect of it was very relevant. Second is the data. Most of the cities, the way we got the data for mobility is mobility surveys from different cities. So we depend on how the city captured the data for us to put them into the system. And that was very challenging because some cities, they put walking, cycling, motorcycles, taxi, BRT, but most of the cities, they don't. So we could not actually distinguish any of the micromobility forms in any of the mobility surveys, except for maybe 2. So that's why we decided to simply add it to the category A and keep it as is. Likely in the future, if micromobility becomes a bigger thing, we will need to redesign. However, if you go to our data set on the citiesmoving.com, you will find that for those cities where the data exists, it is separated into categories. So yeah, for the visuals, we only have 3 because then it's a triangle, right? Like the 3 first. But if you have more modes of transport, then in the data set, you have as many columns as possible. So hopefully that is one way in which we can sort of solve this issue. Thank you for your question.
I actually have a question. This is Jeff. First, an observation. I know, for instance, in India, there was a study that students going to school used up to 37 different modes of transportation to get there. That would be tricky. My question is, you've shown us maps from Jakarta to Kigali and all over Africa and Europe, et cetera. And clearly a lot of the variables you're using are consistent. But I'm wondering how culture impacts choice in these models, because you don't have the same culture and cultural traditions and even habitation patterns and things globally. So how do you account for that when you're thinking of models, or where does that come into the process?
Thank you, Jeff, for the questions. I totally agree that first, there are multimodal shares or multimodal journeys using different modes of transport, because, for instance, public transport requires a bit of active mobility almost always, right? Because nobody lives on top of the metro station. If you park your car here in Mexico City, frequently you will have to park many blocks away because there is no parking space, like in New York City. So it requires a bit of active mobility. If you take a taxi to get to the metro station, then you have these multimodal shares. And I agree that there are all these sort of options. For multimodal shares, depending on the mobility survey, we use the primary mode of transportation. So if you walk to the train station, then usually the mode of transport would be public transport. If you walk towards a parking lot so that you can drive, then it's car, right? So most of the multimodal journeys, we assign them to the bigger category. A and B is B, A and C is C. For the cultural aspects, 100% I agree with you, Jeff. It's been actually quite interesting to discuss the way we observe cars in cities. First, with people in Europe. Second, with people in Latin America. and third with people in the US. In Europe, cars are something to own. Almost every family in Europe owns a car, but the government tells them, don't drive a car. Own a car, buy a car, replace a car, but don't drive it because we want to be sustainable. So Europeans, they pretend to be sustainable because they don't drive the car, but it's just a pretentiousness because owning a car, production of a car, it already takes 17 tons of CO2. Driving is just a small part of the pollution of the car. So when you own a car and you replace it every 3 years, you're already above your budget, and it doesn't matter what. Europeans are happy to own a car and pretend to be sustainable without driving it. People in the US are on the other side. People in the US are happy to own a car and drive it because there is no other option, right? And usually when I have talked to people from the US, they say like, yeah, but there is no other option. And it's true. Oftentimes you don't even have public transport as an option because there are none. Or if you want to, I was close to a metro station in Los Angeles, and you see why people don't use this. Those that get into the public transport in some cities in the US are captive users. That means they are suffering from the worst possible service in the world, and still they have to use the public transport because there is no other option for them. Frequently, it's people that don't have enough money for using a car, or they don't have a driver's license already because they lost it to alcohol or something like that. So those captive users are suffering from the worst possible way of transportation. In some cities, up to 10%. Then you come to Latin America, and in Latin America, the culture tells you car is an aspirational thing. It's like for us going to Starbucks instead of going to a crappy cafe that used to be in the corner. Oh, I aspire to own a car, but it's just because of the status that is giving you. Because poor people don't own a car, wealthy people own a car. I want to own a car and drive it because it gives me the status that I deserve, or that's what many people in Latin America think. Now, what is interesting, Jeff, is that we actually designed cars many, many years ago for moving, right? 100 years ago, the Model T from Ford was designed for moving people. And you see that 100 years later, we have to discuss cars, not for the mobility part, but for everything else, status, production, manufacturing, the economy. Imagine if Germany stopped producing cars, the economy would go bankrupt. So then now we have to discuss cars, not because they move people, but because the economy depends on them, but because of the cultural side, because it's aspirational in Latin America, because it's a necessity in the US, because it's an asset in Europe. Yeah, and that is the tricky side. How do we get rid of cars? Because definitely there is no way that they will be sustainable. So if we want to think of how the world should look like in 50 years, and you want it to be sustainable, it has to be without cars. And that is something that I actually recognize from The Line. The Line, this super crazy city in Saudi Arabia, I think it's crazy because of the shape. I think it's crazy because it's in the middle of the desert. I think it's stupid to make a city that is 170 kilometers long. But something I do recognize is that The Line, when they design it, they know that it's a city that is car-free. They started with a car-free city, knowing that that has to be the way a 21st century city should look like. So there is a positive side to The Line, right? It gave you the plan of a city that has to be without cars. I hope I answered your question. Yeah.
Great. I think that's it.
Okay, was this
Hey,
any
can I
other?
ask my question?
Oh, Nima, yes.
Rafael, my name's Nima Kudva. I teach in the department. And thank you so much for an absolutely wonderful talk. Now, I understood every mathematical piece that you told me in the moment. You asked me to tell you anything about it again, I will not be able to do so. But it's a feat, right? I mean, I'm so struck by first, I think, your joy in your work is so palpable. And thank you for that, because it's wonderful when, that you can communicate that on a flat screen with all the stuff, with all the infographics and everything that you have. But thank you. It was a wonderful talk. And And I was just thinking your response to the student who asked you about travel time and the way you did it was so smart and so wonderful. And then it gave us the explanation in real time of choices we make in Ithaca, right? To shift from sort of when you take public transport or the car. But I had two questions, which are sort of, I think, go back to your training maybe, and thinking much more about mathematics and interdisciplinary kind of work, which is what planners do. So bear with me for a second because my question's going to sprawl by a bit here. So starting with, say, mathematics. There was a recent New York Times op-ed, which I don't know if you saw, and it was something about democracy living and dying by mathematics. Did you see that? It's about a new documentary called Counted Out. And it made actually the argument that one of the reasons it made a civil rights argument, actually, which I thought was really interesting because you were making a sprawl and cart argument. But both of your arguments, yours as well as the one in that op-ed, rested on mathematics. And the argument that the documentary is making is that we have a reduced, what's the word? Literacy with mathematics, and that's one of the reasons why we're not able to actually engage in certain kind of conversations. And the documentaries about civil rights, I think, were making a really important set of arguments about sprawl and cars, right? So for me, in this sort of interdisciplinary mode in which we work in planning, the business of mathematics, especially in the ways in which you were able to bring it to bear on arguments that we have a kind of an intuitive or commonsensical understanding, but you were able to kind of give it, model it, give it numbers, give me really show in very simple ways what one decision could have an impact. Now, it assumes a certain kind of literacy, right? And it assumes for the person who's presenting, your ability to present mathematics is astonishing, actually, right? I mean, no, it's true. And but I want to kind of take it apart a little bit. You've clearly worked on how you communicate. And I think this doesn't just come naturally. People work at being able to communicate in the ways in which you've done. So my question then is about that. It's about the ways in which in planning, right? Or in the work you want to do as an advocate, because you're passionate about this thing. I bet you're bicycling around every city you're in or walking or whatever. And so so my real question is, tell us more about how you've learned to communicate in math. Those fantastic diagrams that you have, who's helping you make them? Have you thought them up? Are you working with a graphic designer? I want to know more about this nitty-gritty detail. And if everybody else is bored by this question, you and I can take it offline. But if people are interested, sure, answer now.
I'm just going to interject to point out we are after 2, so we do need, unfortunately, a relatively brief response.
Definitely. Thank you, Jeff. And Nima, thank you so much for your beautiful question. I really liked it because I appreciate the way you see my presentation. 2 things. I don't believe in a super scientist. The super scientist is that mental mind idea that a person can do everything. No. I don't know anything about biology. I cannot construct a building. I cannot learn law or medicine or chemistry. No, I know maths and I like that, right? But talking to other people, especially for urban planners, is when you realize this actually is a concept that they use. And those interactions, those multidisciplinary interactions for me have been extremely valuable. Because as a mathematician, we see one thing, but it's very limited. We need people who actually understand what does it mean in a city? What does it mean in Africa? What does it mean for a policy? And that has been my experience so far. If you ever come across, and not only for you, Nima, but for everyone, if you ever come across with something that maybe this is too challenging quantitatively, maybe there is some mathematics, why cannot I understand it? No worries, you're not expected to know everything about mathematics, but find one. My email is there, my contact on Twitter, and maybe together we can actually work on something. And that has been my experience so far, where I can bring mathematics to the system, but I cannot bring everything. And it's those interactions that are super beautiful. And in terms of visuals and so on, 1 minute idea that is just a bit of my bio. I ended up studying mathematics in Mexico City. And afterwards, I worked for the police department in Mexico City for 5 years. Working for the police department in Mexico City was extremely exciting because it was working with police officers. I was the only civilian surrounded by police officers. And I realized I can come with the most interesting chart with numbers and equations and systems. They don't care at all. What they care is, what does it mean? How do we eat it? How does it transform into a safer city? And for 5 years, I worked for the police department here in Mexico City, week after week, trying to show them something on how do we predict crime, how do we move, why this metro station. And that was my experience there with the police. How do we, me as a mathematician, my work was systems, equations, data, transform them into something useful for the police. So I believe part of what you're seeing is a person that with 5 years of experience spoke to a person in the police whose experience is how to use a weapon, how to arrest somebody, and how to make the city safer without mathematics, right? So that's why maybe that's how you observe me today and how you observe my research. Thank you, Nima, for your question.
Well,
Thank you
again,
so much.
Rafael.
I'll get in touch with you.
Please.
Thank you again, Rafael. That was, as Nima said, really great presentation, and the clarity and the focus and the breadth of what you're addressing is wonderful. And so on behalf of all of us again, thank you.
Thank you, Rafael.